Hello all, I'm Hema and I'm a PhD student with Brian Corbett in Tyndall National Institute, Ireland. So this talk is going to be about microtranscription technology. This is the outline of the talk. So we'll see a bit about myself and silicon photonics, why photonics, and what are the different integration techniques, and majorly about transubstanting technology, what it is, how it is being used, and what are the work that is currently being done using this technology. So yeah, I did my bachelor's and master's in physics in back in India. And during my master's, I had an opportunity to do an internship in optics. That is where I started my real interest is there in photonics, where I could do my own experiment, and I set up a experiment from scratch, from the base. And I was using a different software called LabVIEW. So it was very fascinating. So you should grab a chance whenever you could get a hands-on experience to do with research. And you doing an internship is already a good start for that. So because of that interest, and I started pursuing my career in photonics. I was working for 3 years in Indian Institute of Science, which is in Bangalore. So this experience gave me uh, intro to how to design a chip and how to manufacture, fabricate a chip, and then test an integrated chip. So those three things, designing, fabricating, and testing, are the three major things that you should know to do uh, photonics. So with that experience, I flew to Ireland last December to pursue PhD, which is my dream for all time. So I landed in Cork, which is a beautiful place, and the people are really nice here to do a PhD. And this is the most interesting topic. I was working back in India in silicon photonics. Now here, this work is about one more step ahead from silicon photonics, how to integrate other active devices or 3-5 materials to silicon. So we'll see a lot about that in further slides. So first, when when electron is used to transmit information, it's called electronics. Similarly, when a photon is used to transmit information, it is called photonics. It's very similar to that. So we are using the same CMOS foundry and the same material silicon that has been used in electronics. The only difference is we are using these both to guide light. And when that happens, it's called silicon photonics. So what is so special about silicon? Why silicon is being used? It's because every material has a particular property called refractive index. It is how fast a light can travel in that medium. If you see silicon, it has a very high refractive index. So it is used with along with silicon dioxide, which is a lower index material. What happens is light gets confined in this higher index material. So what is this rectangular region here is called a waveguide. Waveguide is nothing but uh, similar to a wire which allows a current to flow. It is similar to an electrical wire, but this allows light to flow. Optical mode propagate in this waveguide. These are very tiny features. They are just 500 nanometer in width and 220 nanometer in thickness. So we channel them and make guide light in silicon. And we use the same CMOS foundry as well. So, but everything is good. We can guide light in this medium. The one major drawback is where does the light come from to guide? Because silicon is an indirect bandgap material. Silicon, that means silicon cannot produce light. So somehow the light source has to be integrated to silicon. So that is when different integration techniques comes into play. Either we can have a silicon and epitaxially grow different layers on top of it, which can produce light. That is called epitaxial growth, or wafer bonding. In this technology, we develop different layers of active material or whatever material we want to generate light, and then we bond it to the target material on top of silicon. So if you see, the green layer is on the top here, but it is on the bottom here. So it's taken like this and printed in inverted manner on this. So this is wafer bonding, where entire wafer is bonded to the other material here. Here, this is the major technology that we are going to see. It's called transubsint, where in comparing with this, we are just taking the device, we are manufacturing the device, we are just picking the device from the source wafer or the starting wafer, and in whichever wafer we want to print it, we are placing it on that wafer. It is simply pick and print. So if you see, in comparison to these guys, here the entire wafer is bonded. Here only the device is bonded. So there are a lot of things to do with transubstant technology. We'll see that in steps. So first, from where it started, what is transubstant? In 2006, in University of Illinois, Maytel found that any polymer which has a viscoelastic property can be used for this transubstant. So what is this viscoelasticity? It means when a deformation or during a stress, a material has both viscous and elastic nature. So what are we doing here is, we have this blue wafer is the starting wafer, and these golden color hexagons are the devices. Let's say there's a force between these devices and the blue wafer. Let's call it the force. Let's call the force as X. And And this is a polymer material which we are going to use to take these devices from the wafer. If you can apply a force which is greater than X, you separate the devices from the wafer like this. When the force is greater, you pull the devices from it. And then you go to the wafer where you want to print. Even in that wafer, they'll have a similar attraction. The device will have similar attraction to this bonding wafer. And when you apply a force which is less than this bond, this X is greater such that it pulls the device down to the wafer. So that's what we see here. This green line, what you see is the rate independent adhesion. It doesn't depend on any force. So it is inbuilt. Inbuilt, there's a force of attraction between the device and this wafer. That is what we call rate independent adhesion between the printable device, the golden hexagons here, and its native substrate. That is the screen thing. If the force is greater than that, we pick the device. And if the force is less than that, we print the device. So this is called, so the polymer that we are using is called PDMS. It's a very transparent material. Through the material, you can see the device. So this is very thick PDMS. This is called a PDMS stamp, which is like this. And the PDMS stamp has many PDMS posts. The small rectangular thing you see here is called PDMS post. And these posts are designed according to the devices that you want to pick. We call this as source wafer, from where the devices are taken, and this is called the target wafer. So we, now that we have seen about velocity, if the velocity is greater, around 10 centimeter per second, it picks it up, and if it is less than 1 millimeter per second, the devices are printed from the PDMS to the target wafer. And it is not a fixed number, it varies based on the material and temperature as well. And regarding the PDMS post, as I said, the post is individually designed according to the dimension of the device that we are going to pick, such that if the dimensions are the same, they'll have the maximum contact. That means they are not going to interfere with other devices around. That way it gives a higher yield as well. So the technology is very good to handle a very thin devices as well. Less than 1 micron can also be handled. And the maximum range depends upon the stress and aspect ratio. So this is one of the proven thing, this range. But higher than this is also is possible. So now Once we make the PDMS post and stamp, how many times can we use it? If you see this image, when you pick a device and place it, print it, this is the first time. So similarly, you can print it 25,000 times using the same PDMS post with with fully successive rate. There's no failure for first 25,000 times. So when we are going to print the wafer, then are there any conditions for the wafer that we are going to be printing on the target wafer? The only major thing is it has to be flat, locally flat, so that it can accept the device when it is being printed. So usually the van der Waals force is between the device and the target wafer itself is sufficient. If not, we do a very thin polymer coating or oxygen plasma treatment. This is the actual transabsorption device. I could zoom it in and show you. This is how the device looks. So we have different things like optics, print head, and stage. So via this optics system, you can see the devices below. There's a PDMS post which is mounted here. Below the PDMS post, you can see the device. So we'll first pick the device and print it in a different wafer, which is on the other side. So I have a small video to play on transabsorption. It's from a company called Salient. So what we see here, I'll play it once again so that I could explain. What we see here is in this stage, all the devices are already done. This is the source wafer. All the devices are ready to be taken from this native or source wafer. This is called PDMS stamp, and these are PDMS post, and these are the devices that we are going to pick. But remember, when you can see from the top, the optics is on the top of this. So via PDMS, we can see where the device is. So it is easy for us to locate the device. I'm sorry. Yeah. So once we pick the device, you see a golden thing, the device is being picked. And we go to the target wafer and we place them at any location that we want. So now that we have seen how transabsorption works and all that, to do transabsorption, what we should do when we have to pick a device, what has to be done is the question now. So let's say this is the entire stack or the device that you want to take it. To pick a device, uh, I'll just change to the pointer. Yeah. Okay. To pick the device, we have to create a gap between the device and the film. A little air gap is needed so that the device can be picked. So what we do is the first major step is to incorporate a release layer. So release layer is something, once after you do the device, when you put it inside a chemical, we call it etching. Etching can be done either by using gases, it's called dry etching, or if you use chemicals, it is called wet etch. What it basically does is it consumes the chemical, it consumes the material, one particular material. So we use a chemical such that it consumes this release layer, and the chemical should not affect all the other layers. So when that happens, when this release layer is removed, the device is now floating in the chemical. It can go anywhere. So we need some system to hold the device to the substrate even after this release layer is removed. That is when the second step comes. That is called this encapsulation. Encapsulation is uh, when you prevent the chemical from affecting the sides and the top, and it also this tethering or the anchor system holds this device to the substrate. At the same time, it provides access for the chemicals to access this blue color release layer. So once we have the release layer and we surrounded it with the encapsulation layer such that the chemical does not affect the device, and we have this tethering system or the anchor system. So now when we do wet edge, the chemical will access in between the tethers, and this blue color release layer is removed off. It's literally a bit of a gap between the substrate and the device, but the device is not floating now because it is being anchored. At this stage, we come in with the PDMS stamp, and when we pull with a higher velocity, this anchor gets broken. And then we go to the target substrate and we place the coupons there. So now that we have seen about transcription, there are so many advantages for using this technology. The first thing is we may want to transfer many different things. Let's say a laser or a modulator or a detector. They can be done in different wafers and they can be printed to the one target wafer. Multiple integration from different wafers are possible. And the second major thing is the wafer size need not be the same because usually the 3-5 wafers are smaller. The maximum size is around 100 in dia, but silicon wafers comes almost in 200 to 300 in diameter. They're pretty big. So we don't have any criteria that they both must be of the same size. They can be of different size. Still, you can do this integration process. And area magnification. So what do we mean by that? As I said, 3-5 wafers are small. So the density of the devices is very high in 3-5 wafers. But that need not be the case in the silicon wafer. We can pick just 4 devices from here and place it in any part of this silicon wafer. That's what we mean by area magnification. So if 3-5 wafer looks like this, a silicon wafer can look like that. The space gets multiplied and the density reduces here. And once we pick all the devices, the 3-5 wafers, which are very expensive, can be reused after few processings. If you see in wafer bonding, the wafer has to be bonded to a similar size wafer. That is one advantage that we have over wafer bonding. And second thing is, there, once you bond the wafer has to be etched away. But here in transfer print, we are not etching away the wafer. We can reuse the 3-5 wafer after doing the transfer print of the devices. And the biggest thing is it's a room temperature process. So if you had done any process earlier, which involves, say, some metal, and the metal won't get melted or the doping may not change because it is done in room temperature. So the device from this stage can be transfer printed at any level. Either you can fully develop the device and then print, or you can do only the basic layers here, print it here, and finalize your fabrication in the silicon wafer as well. It has a very high process yield and placement accuracy. So what do I mean by placement accuracy is we can transfer the wafer and then you can devise your waveguides. So in that way, it's the placement accuracy is very high. The major thing is you can do parallel process. That means even hundreds of devices can be picked and placed at the same time. So how long does it take? For one whole pick and print process, it takes only 40 seconds. So in that 40 seconds, you can pick and place either one or hundreds of devices. It all takes the same time. These are some of the examples of the work that are done using transubstance technology. This is from my senior Lagathar Loy in Tyndall National Institute. So what he has done is he has transubstanted an indium phosphide laser here. So since it's a laser, one side is fully reflecting and we have the light coming out from this eye. And he has a polymer. So he has done few dimensional changes such that the light comes from this region to the soil below. The light is guided like this. So this is where transubstance comes in. They do all these structures first, and then this entire blue block is developed in a different source wafer and it is printed on top of this. This is a similar technology called Fabry cathode laser, where in silicon they have created a cavity and they transubstanted the device. So here we see a similar thing for the detectors. So this is how the detector look before in the source wafer. You can clearly see these small rectangular things holding to all the four sides. This is called the ether. So once when we pull the device, this gets broken off. The ether gets broken off, and then it enables us to pick and send to the other. So this is where my work stands in comparison to others. So what I have is I have a soy wafer. Soy means silicon on insulator. So we have silicon. The insulator here is silicon dioxide. So in the soy wafer, I create a small trench like this. Only the soy is opened up. And a device, an active device, is transubstanted onto this. This can be anything. It could be a laser or a detector or anything. And there is a gap. So once after I do this transubstanting, there's a gap between this silicon and the transubstanted device. So what happens is when the light comes, as I said, you can devise a waveguide. In the waveguide, when the light comes, suddenly it sees a difference in the refractive index. This is silicon, it has a high refractive index, and this is air, which has an index of 1. So it is similar to a case like when a water is flowing in a hose and suddenly there's a break. The water splashes on all the sides, the water leaks. Exactly that's what happens here. The optical mode or the light that is coming like this, suddenly it sees a drastic index difference. So the light leaks at this point, at the gap between the transubstanted device and the silicon here. We don't want that to happen. So we do some trick to fill in this layer with a similar index material. So we are thinking about using amorphous silicon, which has almost same index as silicon. This is called plasma enhanced chemical vapor deposition techniques. It's one of the method to fill in or to deposit material. So after that, we create a waveguide and taper. These are the things that we use to guide light. So this is how it looks. This is the overall plan for the entire PhD. And presently, because of lockdown, what I'm doing is some simulation work, which I can do with my laptop in my room. And so in simulation, what we do is fabrication is a very expensive process. So we want to figure out all the dimensions before we go for fabrication. So I play with the thickness, width, and all these parameters to guide light. So what I've shown here is when I change this edge depth means if silicon is consumed in the sides, now you see only 100 nanometer silicon here. That means it is etched for 300 nanometers. The entire silicon is 400 nanometer. Now I have etched 300 nanometer here. That means the silicon is consumed, so it is air. So when I do that 300 nanometer etch, it is confined in a better way. Even good, if I etch this also, it is confined even more better. So I'm doing few simulations to check how to confine and guide and manipulate light in the way that we want it to behave in this device. So the future work is going to be about fabricating this device. There are a few challenges that we see ahead. It's like when we do this amorphous silicon deposition, there might be some void. As I said, this creates an intake difference. That means there's a leakage, and the sidewalls uh, could be porous. So you may have to optimize the parameters for this deposition. It's mostly with this process, majorly how we are going to fill in with the substance which has a similar index as this. That is the main concern here. And one more challenge is when we are filling in between the silicon and the active, when I'm depositing a amorphous silicon layer, if this is 400 nanometer thick I'm depositing, the same thickness is deposited on top here and here. So we want to remove this excess deposited material. That is one of the third challenge. So this is all about transabsorption technology and a little bit about my work. So that is it for now. And if you have any queries, please feel free to contact me at this email ID. I would be more than happy to help you out. Thank you for listening. Bye bye.